So I want to talk about the argument principle. So it says the following. It says that if f so if omega, let's say, okay, so let's if D is a disk, let's say omega is a region, with D a disk, okay, and F a holomorphic function on omega, then we have the following thing. So the number, so this is equal to the number of zeros of F inside D. We can compute this via a formula. So it's 1 over 2 pi I, the integral over the boundary of the curve, or boundary of the disk, and then we take a logarithmic derivative here. This is what the argument principle says, so for a holomorphic function. Okay, so let me give the idea first. So here's the idea of the argument principle. So let's consider a polynomial like this, C. Okay, and I want to look at what happens to, so here's the map F. Okay, and then here's one copy of the complex numbers here. And here's another copy. And let's take a point here, Z. And let's look and let's suppose that our points are like this. A, B, C, D, like so. And so what I want to do is I want to look at the image of, let's say, a curve here under this map. So let's call this gamma. So I claim that f of gamma looks something like this. So here's 0. And I claim that it does something like this. So 1, 2, 3, 4. Okay? So it goes like this, f of gamma. So how do I know this? So here, what we can do is we can look at a bunch of, I'm going to draw here these vectors. This is the vector z minus a. This is the vector z minus b. This is the vector z minus c. And this vector here, this is the vector z minus d. And each of these has an associated angle with it. There's, let me draw in the angles here. There's this angle alpha, there's this angle beta, there's this angle gamma, and there's this angle delta here. So what I'm really writing is that, so for example, z minus a is equal to some magnitude, and then we have e to the I alpha. And z minus b is the magnitude, e to the I beta, and so on and so forth. So this is equal to z minus c, z minus d, okay? So this is this magnitude, I gamma, e to the I delta. Okay, and when we multiply these guys together here, so what we're doing is f, it takes all these vectors and it multiplies them all together. And when we multiply the numbers, right, what will happen is that we add, okay, we also know that A, B, C, and D, they all go to 0. And that these guys, all the angles get multiplied together, right? And so whenever you pass around once around this circle here, when you pass around this circle like so, right, one pass here, so what will happen is that this angle does, alpha does the 2 pi rotation, beta does the 2 pi rotation, gamma does the 2 pi rotation, and delta does the 2 pi rotation. And when we multiply all these numbers together here, we get alpha plus beta plus gamma plus delta. And that's why this thing here, so this thing, let's say, I don't know, maybe it'll be like this. So I've drawn maybe a quarter of a thing. It actually will give us like a full rotation there. Yeah, so this is one of the ideas that's driving this thing, that the winding number here can detect the number of zeros inside of this. Explicitly, the contour in the picture there. So what we've done is so what have we done? We're looking at this contour here. We had our original gamma here over f of z dz. Okay, and this guy here is really the integral from 0 to 1. So this is a closed loop. And this is f prime of gamma of t, gamma prime of t, over f of gamma of t, dt. This thing here, well, this guy here is the integral from 0 to 1 of this d dt of f of gamma of t over f of gamma of t dt. So if we let gamma of tilde, so this thing here, this is the integral of gamma tilde dz over z, where gamma tilde, well, this is really the image of f of gamma, but let's write it like this. F of gamma tilde of t is equal to f of gamma of t. Okay, so if we go back to this, so this guy, now we've written, what we started with is we started with the argument on this side, so the original integral on this side, and this integral turns out to be just another contour integral here. And this is the winding number of f of gamma around 0. Okay, so this is the idea behind the theorem here. So this is the number of zeros inside. So let's give a full proof of the argument principle. So, all right, so let's write, so we're going to start with an arbitrary holomorphic function, right, f of z, and we can write f of z is equal to z minus a1 all the way up to z minus ar g of z, where g of z is a holomorphic function on omega. It's nowhere vanishing. So this follows from the structure of analytic functions, right? So this was that zeros of analytic functions are isolated. So these are the zeros of f inside the region D. Okay? So f, now we do a computation. So this is log of f. So this is the logarithmic derivative. I was calling it the logarithmic derivative. And this is just, the sum of sums of log like so, and this is equal to the sum plus the logarithmic derivative here of this guy, and so this is the sum of 1 over z minus aj, j is equal to 1 up to r, plus g prime z over g of z. And we want to observe that this function here, so this guy here, this guy's analytic on D. So the denominator is not going to be 0 on D. So that's what's nice about this. Okay, so now we just compute a little bit more. So therefore, this integral of, so this is equal to 1 over 2 pi I times the sum so this is a simple contour, so we know that it's going to wind once. This guy was analytic here. So by analyticity, this guy goes to 0. This is Cauchy. And these guys here are a bunch of winding numbers. So we could distribute the 1 over 2 pi I. So this is the sum n dd aj, like so. Okay, and that proves the theorem. So this is 1 for this is 1 because since r here, since gamma, since this guy here is simple, and aj is in the interior of this guy. Well, it's in D. Okay, I guess you could call this DD plus if we wanted to. Okay, so that's the proof of the argument principle. Okay, so there's a souped up version. So remarks / enhancements. Enhancements. First, the obvious thing is that a more general version holds with winding numbers. But we don't really, I mean, I've never used this in my life. Okay, so I'm just not even going to state it. Okay, so you could make your curve crazy, and then you could count, instead of just counting the zeros inside, you could count them with how much they wind. Okay? The other thing is that if one can replace f of z holomorphic with f of z meromorphic. And in this case, we get that 1 over 2 pi I here, dt, so this is the zeros of f minus the poles of f. Okay? So these are poles, and these are zeros. Okay, this is an interesting formula here. And the idea, I guess, is that you do the local factorization like we did before. We do the exact same factorization, but now you factor the poles as well. So in the new version, you do this, you factor with poles. Okay, and poles according to their multiplicity. All right, and then once you have those poles in the denominator, you get a contribution from this negative part. Lastly, this gives another important variant. So this gives previously we defined the ramification index, or the order of vanishing, order / multiplicity of a value, right? And we said, we looked at the order at z is equal to a of f of z minus f of a is the multiplicity of the value. Okay? So this is this kind of analytic multiplicity. And it tells you how many times f of z is equal to f of a at a with multiplicity. We can now define a topological multiplicity. So the topological multiplicity is this thing. So this is the topological multiplicity. So one can see that this thing here is so one sees, so here d let me just write this. So if this is the boundary here, so then this guy here, sorry, we're going to call this gamma. So this is equal to okay, and so this is the boundary of the disk. Okay, so this is what this is, and this, I showed how to relate these two guys in the previous example. So this is related to this thing here. So instead of so what we actually do is you shrink around a point. Okay, so here, to define this topological multiplicity, what you do is you take a point here, here, and then you look at a really, really small, so super small guy here, and you map it via f, and what'll happen is that this thing will maybe do something like this. Okay, so the picture that I've drawn is something with multiplicity 2. Okay, so if this is a, and this is f of a, So the topological multiplicity here we've drawn is, this has topological multiplicity 2. So, okay, so here's a claim, is that the topological multiplicity is equal to the analytic multiplicity. Okay. It's kind of messed up, but you understand what I'm saying. Okay? And so the idea is that, here's the idea. So the topological mult, well, it's just kind of easy. It's almost tautological, right? So this guy here is 1 over 2 pi I. So this is I guess, at a point A. So this is a little neighborhood at around A of, so this is the winding number. But we also know from the argument principle, so this is the winding number. All right, and this is also equal to, from the argument principle, the zeros of f of z minus f of a. Okay, and with multiplicity. Analytic multiplicity. Okay, and well, this is exactly minus f of a. And so this is equal to the analytic multiplicity. Okay, so that gives us 2 ways of talking about the multiplicities.